Hello, I'm Ichi Watanabe from Frontier Laboratories. Today, I will give you a talk about Py-GCMS applications in environmental analysis for VOCs and microplastics. Here is today's agenda. I start with a brief explanation of the fundamentals of pyrolysis, then talk about different applications using Py-GCMS system. So throughout this talk, you will find out the wide applicability of the pyrolysis techniques to environmental samples. This is a simple example of pyrolysis using butane, which is used for gas lighters. This is a chemical structure of butane. Now, when you burn or pyrolyze butane gas under air, it turns into CO2 and H2O. How about pyrolyzing butane gas under helium? It breaks down into smaller molecular structures like methane, ethylene, and so on. How about polyethylene, which has a much higher molecular weight than butane? It is going to break down into smaller molecular structures like butane. Okay, let's look at typical pyrograms of polymers. These are pyrograms of polyethylene, polypropylene, polystyrene, and SBR. A pyrogram is a chromatogram of the pyrolysates obtained by pyrolysis. So comparing these four pyrograms, you can see differences in peak patterns. Let's look at polyethylene. You see many peaks, which are hydrocarbons. And what about the polystyrene? You see three major peaks only, and these are styrene monomer, dimer, and trimer. Since pyrograms reflect the original chemical structure of samples, depending on polymer type, each polymer shows unique peak pattern like human fingerprints. Also, usually each polymer has its own characteristic pyrolyzed peaks. So peak pattern and or characteristic peaks on pyrogram will tell a polymer type. Pyrolysis GCMS is a very powerful tool to characterize polymer materials. These are the main purposes to use this system. Identification of polymeric materials, such as identification of unknown materials, or to see the structural characterization of polymers, mechanisms and kinetics of polymer degradation, and qualitative and quantitative analysis of additives contained in polymeric materials. Let's look at the typical system configuration of Py-GCMS. A typical Py-GCMS system is a pyrolyzer furnace installed in the inlet of GCMS system. Depending on the selection of a non-stationary phase 3-meter column or GC separation column, either thermal or separation analysis is applicable. The thermal analysis is called evolved gas analysis, EGAMS, which is similar to TGA. The sample is heated at a certain ramp rate in the pyrolyzer, and the gas generated at each temperature is monitored by the MS detector. This is a typical EGA profile. The horizontal axis is pyrolyzer furnace temperature, and vertical axis is peak intensity. So this profile provides information on at what temperature the additives are vaporized, and at what temperature the polymer components are pyrolyzed or decomposed. And for separation analysis, basically three methods are applicable: flash pyrolysis, thermal desorption, and the combination of flash pyrolysis thermal desorption called double shot GCMS. The The thermal desorption GCMS, the sample is heated at a certain ramp rate, and information on the additive components is obtained. In the flash pyrolysis, a sample is instantaneously pyrolyzed at high temperatures such as 600, and both polymer and additives components are obtained. Double shot GCMS is a combination of these flash pyrolysis and thermal desorption. Actually, thermal desorption and followed by pyrolysis. So if you want to characterize an unknown polymer sample, you use the double shot techniques. So you first thermal desorb your sample, then you do the flash pyrolysis, so that you will be able to obtain additives and polymer information. This slide explains the sample preparation for Py-GCMS. Basically, any sample form like solid, liquid, gas is analyzable. In step 1, so solid samples are cut into small pieces by a knife or file or cryo-milled. If samples are soluble, dissolve them in a solvent. If it is a seed-type sample, just punch it out. In the step 2, just place a sample in a sample cup and measure the weight. Usually 0.1 milligram sample is recommended. So no solvent extraction is required. Then step 3, drop the sample cup into the pyrolyzer furnace and start GCMS measurement. Very simple step. From this slide, I will introduce 3 different examples. The first application example is the analysis of phthalates of Rowe's directive using Py-GCMS system. So what is EU Rowe's directive? Rowe's stands for Restriction of Hazardous Substances. So the Rowe's directive aims to prevent the risks posed to human health and the environmental related to the management of electrical and electronic waste or equipment. So the use of 4 phthalates has come into force in July 2019. So this is a list of restricted substances in the Rowe's directive. And phthalates, so each phthalates must be below 1000 ppm. In March 2017, the thermal desorption GCMS using pyrolyzer was adopted as the official method and approved by IEC for the analysis of certain phthalates in electrotechnical products regulated by the Rowe's directive. The pyrolyzer TD GCMS method is suitable for semi-quantification and screening of DIBP, DBP, BBP, DEHP, DNOP, DINP, and DIDP in the range of 100 ppm to 2000 ppm. This is an overview of analytical procedure. As I explained, simply cut your sample into small pieces with a knife and place them in a sample cup and measure the weight. Then set the sample cup on a pyrolyzer. The sample cup is heated inside the pyrolyzer and phthalates are thermally dissolved. Let's take a closer look at what is going on inside the pyrolyzer furnace. The sample cup stays at the sample cup waiting position before analysis. When the pyrolyzer temperature is ready, the sample cup is introduced into the center of the pyrolyzer and heated at a certain temperature. Phthalates are thermally then dissolved from the sample and they are swept into a GC separation column biocarrier gas. Then these phthalates are separated in the separation column and detected as a peak. Then quantify them by software. This is a TIC chromatogram of standard sample of the phthalates in PVC with DINCH. DINCH is a non-phthalate plasticizer. These are EIC of each phthalate. You can see that each phthalate is well separated and appears in a different retention time. It is noted that a non-phthalate plasticizer, so in this case DINCH, is commonly used in percentage levels, and it coelutes with several of the restricted phthalates. This is the reason why it is necessary to find characteristic ions to use for quantification. Here's another example of the quantitation of phthalates. The sample is a plastic toy as shown in the picture. Red part, blue part, and yellow part were analyzed, and we found out that the concentration is different by part. So when you analyze your sample, it is important to consider sample homogeneity. For instance, you can use a cryomill or a Granger sample if the quantitation value is going to represent the entire sample. Otherwise, you won't be able to get good reproducibility. This is just a reference. This is a list of phthalates that have been determined by Py-GCMS system using the thermal desorption technique. So in addition to the 7 phthalates, these phthalates can be analyzed by Py-GCMS system. The next application example is the application of VOCs using the Py-GCMS system and Magic ChemSolver. Magic ChemSolver is a solid phase extraction device. Solid phase extraction is a sample preparation technique used to concentrate and purify samples before analysis. There are 2 types of Magic ChemSolvers available, depending on polarity. One is a polar type, called MC-PEG, and another is non-polar type, called MC-PDMS. MC-PEG has a 30 micrometer of close-linked PEG solid phase coated on a deactivated stainless steel tube. MC-PDMS has a 500 micrometer of cross-linked PDMS solid phase coated on a deactivated stainless steel tube as well. Their size is small enough to use with a pyrolyzer or other thermal desorption devices. In general, there are 3 sampling techniques: direct immersion, headspace, and air sampling. For direct immersion, Magic ChemSolver is immersed in a liquid sample for a certain time. For headspace, Magic ChemSolver is suspended and exposed to volatiles derived from a solid phase placed in a sample vial. The vial may be heated depending on the target compounds. For air sampling, Magic ChemSolver placed in a sample tube is set to an air pump sampling device. As the device sucks up the air, VOCs absorbed on the Magic ChemSolver in the sample tube. I will show some example of analysis of VOCs using these techniques. This is an analytical condition used for the applications. Let's look at system configuration. Place a Magic ChemSolver in the pyrolyzer and do the thermal desorption. The thermally dissolved compounds are then cryo-trapped at the top of the separation column before analysis. Once thermal desorption is completed, GCMS measurement starts. So it is noted that because the VOCs are of course low boiling compounds volatiles, to obtain a sharp peak for the VOCs, we use the cryofocusing device, microjet cryotrap, during the thermal desorption of the sample. This is an example of apple juice using a direct immersion sampling technique. The top one is MC-PEG and the bottom one is MC-PDMS result. You can see that esters are selectively excluded on MC-PEGs. This is an example of blue cheese using the headspace sampling technique. The top one is again MC-PEG, bottom one is MC-PDMS result. You can see that the carboxylic acids are mainly observed on MC-PEG, while esters and ketones are mainly observed in PDMS. This is an example of air in a new car using an air sampling technique. The top one is MC-PEG and bottom one is the MC-PDMS result. Let's look at MC-PEG's result that carboxylic acid, alcohols, aldehydes, and phenols are mainly observed on MC-PEGs. This is an example of the analysis of other components in recycled resin pellets. The other components from a polypropylene pellet, which was recycled from wax and detergent containers, are extracted by MC-PDMS and MC-PEG using the headspace sampling technique, and the MCs were analyzed by thermal desorption GCMS using a separation column with low polarity. These are results, and this is a list of detected major components. So limonene, a typical citrus odor component, was detected in a large quantity by the MC-PDMS. On the other hand, with MC-PEG, many polar compounds, such as alcohols and carboxylic acids containing trace amount of other components, were detected. This slide shows analysis of other components in recycled resin pellets. So the same sample, same procedures, but in this time we use a high polarity separation column. As in the previous slide, limonene was detected mostly by the MC-PDMS. On the other hand, more polar compounds, including other components, were detected by MC-PEG. So in conclusion, solid phase extraction both with non-polar and polar magic chem solvers of MC-PDMS, MC-PEG, and thermal desorption GCMS using Py-GCMS system allowed the detection of both non-polar and polar other components from recycled polypropylene pellets. The last application example is the analysis of microplastics using Py-GCMS system. I'm sure that most of you have heard of microplastics in the environment. As shown in the picture, environmental microplastics are different in surface area, shape, size, dispersion, diameter, color, and so on. The popular analytical methods for environmental microplastics are spectroscopic technique, such as micro FTR, ATR, or micro Raman, and then also Py-GCMS technique. The right side is a summary of features and challenges for both methods. Major difference is that the spectroscopic technique provides quantitative information based on number of particles in a square meter, whereas Py-GCMS technique provides mass-based quantitative information. In other words, Py-GCMS method is a complementary method to spectroscopic technique and vice versa. Unlike industrial polymer products, analysis of environmental microplastics using Py-GCMS faced these challenges. For instance, we don't know what kind of organics and inorganics are contained in an environmental sample. We have to consider the secondary reactions among pyrolysates due to the unknown organics and inorganics. So we overcame these challenges and developed an analytical method for microplastics analysis using Py-GCMS system. So the details are reported in the journal papers here. If you are interested, please find more information. Let's talk about the workflow of microplastics analysis by Py-GCMS system. The workflow is divided into 3 parts: sample prep, Py-GCMS measurement, and data analysis. For the sample preparation, first you prepare a calibration standard sample to create calibration curve. Frontier Lab commercialized a microplastic calibration standard, which is a mixture of 12 polymers with an inorganic dilute. 12 polymers are polyethylene, PP, PS, ABS, SBR, PMMA, PC, PVC, polyurethane, PET, nylon 6, nylon 6. For environmental samples, pre-treat your sample by removing proteins, organics, and inorganics as much as possible. Then homogenize the samples. Sample homogeneity and particle size are key for the good reproducibility of your data. We usually use a cryomill to pulverize plastic samples. This is a picture of the microplastic sample before and after cryomill. So when you measure the sample weight, we recommend start with 0.1 milligram or less. This is because depending on the type of plastics, pyrolyzing too much sample amount will lead to producing many pyrolyzed peaks, which may cause peak saturation and contamination of the system. The next is Py-GCMS measurement. You place the sample cup on the sample tray of the autoshot sampler as in the picture. A maximum of 48 samples can be loaded. Then you input an analytical condition. We already optimized the analytical condition if you use our system. So once the system is ready, then start Py-GCMS measurement. This is a diagram of microplastics calibration standard sample. You see many different pyrolyzed peaks on these diagrams. For data analysis, look for a characteristic ion of pyrolyzed peaks of each polymer and then calculate quantitation values for each polymer. To calculate quantitation values for each polymer, F-Search MPs 2.0 can automate qualification and quantification work. F-Search MP's operational procedure follows these 4 steps. So for more details, please refer to this reference. So from here, using the Py-GCMS system and software F-Search MPs, we run different environmental samples and identify and quantify microplastics. So the first analysis example is the environmental plastics collected in Osaka Bay provided by Professor Tanaka in Kyoto University, Japan. So we analyze these 4 samples, sample A to D, and identify what types of plastics are they. So it is interesting to share that sample B was presumed to be EPDM as a result of FTIR analysis, but it was found by Py-GCMS that it was a blended polymer of SBR and natural rubber. The next is the analysis of the environmental samples collected in the Pacific Ocean off the coast of northeast Japan, which was provided by Professor Isobe in Kyushu University. So those floating on the surface of the sea were collected by a new stone net that was horizontally drawn at the surface layer of 1 meter, then sieved to certain particle size, and these samples were cryomilled and then pyrolyzed. As a result, it was found that the main components were polyethylene and polypropylene, and the composition ratio was also found from the quantification values with good reproducibility. When measuring environmental samples, it is necessary to consider the effects of the matrix on inorganic and organic substances. The top one is a pyogram of 12 mixed microplastic sample and pine good, and the lower one is a pyogram of only the 12 mixed microplastic sample. This is a plot of the relationship between peak area of the characteristic ion of polyethylene versus quantification value calculated from pyogram of these 2 samples. As observed, the calibration curve did not overlap between polymer mixture sample only and the polymer mixture sample and pine good. It is presumed that a secondary reaction occurred among pyrolyzed components or compounds of polymers and pine good. The right pyogram is environmental sediment samples in the ocean. The data was provided by Dr. Barbara of the University of Oldenburg, Germany. So many peaks derived from not only polymers but also crude oil were detected from this sample. So there are unknown organic and inorganic components in environmental samples. So you can see the importance of the sample pre-treatment before analysis to obtain a good chromatographic peak shape and suppress secondary reactions among samples. There has been a standardized method under discussion in ASTM method. If you are interested in microplastic analysis, this may be a good reference for your future work. In this talk, I introduce 3 examples using Py-GCMS system with different techniques. Analysis of phthalates used thermal desorption technique. Analysis of VOCs used a magic chemisolvers with thermal desorption technique. And the last one, analysis of microplastics used flash pyrolysis technique. So throughout this talk, hope you understand that Py-GCMS system has a wide range of applications. Thank you very much for your attention and hope my talk will be helpful for your future work. Thank you.